All right, so let's keep going here. So I want to do a quick review of circuit analysis. I said we're not doing analog circuits in here, but I lied. There's one part in one of the labs where I want to do some analog circuits, and it will be useful to keep in mind what's actually going on, because even though we have a digital circuit, it's still in an analog universe, right? So even though we're saying this is either 5 volts or 0 volts, it's still, you know, analog inside. We're just building fancy circuits that force the voltage to tend to be either high or low. But in fact, when the output changes from a 0 to a 1, it doesn't jump from 0 volts to 5 volts, it slowly rises. Slowly meaning a few nanoseconds, billionths of a second. But it's still an analog circuit, so it's useful to sort of keep in mind what's going on in the analog realm. So let me tell you what your first homework problem is, and we'll work through it, and I want to make sure people are up to speed on this. So see if this is familiar. So here's a voltage source. Oh yeah, I changed the odds, sorry. Thank you. All right, so here's a voltage source, and here's a resistor. And let's say this is 1 ohm. And we want to analyze this circuit. It means we want to figure out the voltages and currents, right? So for me, it's easier to think of current coming out of the positive of a source, but you can draw your current any way you want. But I'm just going to draw an arrow here and say this is I. Okay, that's the current. And current does not change when you go through a resistor. Okay, voltage changes, but if this is I up here, it's also I around this corner. It's also I going through this resistor. It's I down here. It's I around that corner. It's I everywhere. Right? The current is constant around a loop. So what is Ohm's law? V equals IR. All right, so here we have a resistor, and we have some current I going through it. We have a resistance of 1 ohm. Do we know what the voltage is across this resistor? Yeah, so wires don't change voltage. Since this is 9 volts between here and here, it's also 9 volts between here and here, here and here, here and here, here and here. So this is 9 volts going across that resistor. So once you have a resistor and you know at least 2 of voltage, current, and resistance, you can use Ohm's law. So in this case, I know that voltage is 9 volts. I don't know what current is. I'm just calling that I. I know the resistance is 1. I've got an equation, 9 equals I times 1. I can solve that for I. I is equal to 9. And if this is volts and ohms, current's going to be amps. Okay, so is that sort of familiar to everybody? All right, so slightly more complex. Pair of resistors, 1 ohm and 2 ohm. So again, I is flowing through here, and I is going to be constant. Do we know directly from looking at this what the voltage across this resistor or that resistor is? No. But we know the voltage from here to here is 9 volts, because that's, 9 volts. Wires don't change voltage. So we know the voltage from here to here is 9 volts, but that doesn't tell us directly what the voltage is across each of these resistors. So what's the trick we do to analyze this circuit? Add the 2 resistors. Find an equivalent circuit, which with series resistors we can just add them together, and we can say, this circuit looks kind of like this. And we still have the same current I coming out here, right? Writing this as a combined 3 ohms doesn't change this current. But now we got the problem we just did. right? We know that we have a current I flowing through here. We know we have 9 volts here. V equals IR, so 9 is equal to I times 3. I is equal to 9 over 3, which is 3 amps. Now we back up to our original circuit, and we say, you know, since I is equal to 3 amps, this is 3 amps here, this is 3 amps here. Well, now we know the current and the resistance, we can find voltage. So we know V equals I times R. So up here we can say V is equal to 3 times 1, which is 3 volts. And here we can say V is equal to current times resistance, which gives us 6 volts. And beautifully, if we take 3 volts and 6 volts and we add those together, what do we get? We get 9 volts. Our voltages all add up. Okay, so this is as sophisticated as we're going to get, and I think in Lab 2 there's a question set at the end where you're playing with series and parallel resistors, and you have to do this kind of calculation. Okay, and there might be a circuit that you build to go with it, but that's as deep as we go. Okay, but I posted a homework question that I'd like you to do by Thursday, which is basically this. Okay, so let me show you your homework. So homework 1, sketch a circuit containing a 5-volt voltage source in series with a 2K and 3K ohm resistor. So K is just 1,000. So it's going to be the same thing, except this is 5 volts. This is 2,000 ohms, this is 3,000 ohms. Okay, but exactly the same procedure, and I'm telling you what the procedure is in here. Sketch an equivalent circuit with a single resistor. So add those resistors together, that'll be a 5,000 ohm resistor. Use that answer to calculate the current coming from the voltage source, find your I. Right, 5 volts equals 5,000 times I, divide, that gives you I. And then, based on that, what's the current through each resistor? It's exactly the same current coming out of the voltage source, because current is constant, right? And then, last step, once you know what that current is, and you already know the resistance, use Ohm's law to find the voltage. So it's a direct repeat of the problem we just did, okay? The reason I'm giving this to you, though, is because I'm going to be picky about how you write up homework. So here's a guide to writing up homework. And let me just pull it off of my files instead of reading it through Canvas. All right, I fit this all on one page, so it's not too long and wordy. So general guidelines, okay? Basically, we're after neatness, okay? I don't have the best handwriting in the world, so I sympathize with less than perfect handwriting. But neatness means don't scribble, right? If you need to remove something, draw a single line through it, okay? Don't do a big blob that goes into your good work and so on and so forth. Ideally, work out your problems on scratch paper or a whiteboard or something, because a lot of these problems, especially as we get later in the course, will take some trial and error. And if you try to do the actual trial and error on your homework becomes very difficult to follow. And if I'm trying to give you partial credit, I might start following your work, see that you'd made a mistake, and that's where I sort of base your grade. And maybe you corrected that mistake later on, right? So if you do this on scratch work and then copy it over, that's going to be easier to read. It's going to be a better chance of getting partial credit and such. And it's good practice, right? And if you're copying it over and you make a mistake, you wrote a 5 instead of a 6 or something, right? Don't panic. But as opposed to doing all the trial and error and missteps on the thing you actually turn in. I definitely recommend a good number 2 pencil with a nice sharpener, so that you can write and you can erase, but so it's easy to read. Don't use, like a 9H pencil. It's impossible to read. And avoid pen unless you're really confident that you can work and never make a mistake. Okay. Print instead of cursive writing. 8.5 by 11 paper, clean edges, nice corners. Okay. You can either use paper with lines on it, or you can use, just plain printer paper with no lines.
I like graphing paper. Does that work?
Graphing paper is fine. Unlined is fine. Lines are fine. Engineering paper is very fine. You can buy pads of it in the bookstore, and it's got different sections to it and stuff. But basically, I don't want homework being turned in a bunch of different sizes and frizzy edges and things like that. Not only because it makes it more difficult for me to go through them, but also people's papers get caught or lost in other people's papers and things like that. So 8.5 by 11, which is letter size. I'd like you to do your problems in order, okay, numeric order, because I'm usually looking for particular problems, and it's just nicer if it goes 1, 2, 3, 4, 5, instead of 1, 5, 3, 2, rest of problem 5, sum of problem 1, and so on. And I'd like you to do single-sided. I apologize to the trees, we'll recycle, but just right on the front, because depending on type of paper you're using, sometimes everything bleeds through and it becomes even harder to read. So the actual page layout, okay, I would have snickered so badly at my teachers if they had done this to me when I was in school, but I sympathize with them now. So top of the page, I want the following information. I want the staple in the upper left corner. Okay, so staple goes up here, and yeah, I shouldn't have to say that, but sometimes I get staples over here, and I've got to actually flip this to see what the problem number was and stuff like that. I mentioned this to one class, and someone they managed to get a staple right in the middle, and they turned that in just to be funny. So staple in the upper left corner. Okay, followed by your name, and I would like your full name, first name, followed by last name. Okay, no initials, please, unless that's how you actually go by your name. But I get people with the same last name, and I get people who use a different name from what's in Canvas, and they just put down their initial, and it's I have no idea who this person is. And it's actually caused some problems in the past. So name goes next to that. And then the class, that's just Engineering 250. And then the homework number, so something like homework 1. And then the date. And then in the upper right corner, the page number. And if you've got 5 pages, right, your first page would be 1/5. So something like that, but better focused. All right, so that's at the top, and there's nothing else on the top line of what you turn in. And that really helps me. This is not such a huge class, right? But I have one class with 60-some people in it, and it can take a significant amount of time just trying to figure out whose paper is each if I have to find it on different.
So you want to all go across, not in?
All going across top of the page.
Okay.
And put that on every page in case they become unstapled. If you want to put in a middle initial or something like that, I'm okay with that. But just make sure it's first name, last name, especially until I get to know you. All right, left margin of the page, wherever you think of the left margin. So, some area, if you've got paper with a margin marked on it, like engineering paper, that's fine. If not, just imagine some margin over here. I don't want to see anything in here except problem numbers. Okay, so you can do problem 1A. And 1B and 1C. All right, but keep that margin clear other than the problem numbers. so that it's easy to identify what problem is which. Other engineering courses will tell you only one problem per page. I'm not going to do that because I'm already doing single-sided. So you can do multiple problems per page, okay, as long as you got those problem numbers on the left side. Okay, most important thing, your work should be organized. So ideally, you know, where I say 1A, this is the beginning of the work for problem 1A. And what comes below it comes next logically in my stream of work, and what comes next. And down at the bottom is my answer, right? And avoid, you know, working down here and then coming up and working in this next imaginary column and then working over here and then putting the answer back over here on the left or something like that, right? Try to make it flow logically. And at the very bottom, circle your answer. So that if I look at it, what I should see is a problem number, a bunch of work, and then a circled answer, and then a bunch of work and a circled answer, and so on. Does that make sense? So I'll cut you a lot of slack. The main reason for homework 1, it's a straightforward assignment in the sense that, you know, we already did it right here, and you've done it in 120. So it's not so much question of getting the engineering right. I really want to see how this layout works, right, and make sure that people understand this. So if it's not the way that I'm asking for, right, I'm not going to ding you 100%. I'll just put some comments on it and say, you know, make sure your name is on every page or whatever. So this is just kind of a warm-up homework exercise, so no stress. All right, so I'd like that by Thursday. Yeah, so that's due April 11th, so that's Thursday. Homework, generally, I want collected in the beginning of class. So when you come in, go ahead and drop that off. If you come into class late, just come on up and drop it off up here. And don't hold on to it until the break and then say, oh, I got my homework, by the way, because we've probably already talked about it. So, all right, any questions about that? All right, if you have problems or questions in general with this course, you got a few options for help. One is my office hours, right, which I gave you a link to it, but if you just want to see them here, mostly mornings, but different hours. So Mondays it's just at 11, Tuesdays it's at 9 and 11, Wednesdays I got 8 till 10, and then Thursday looks like Tuesday, and Friday is just at 9. So depending on when you have other things going on in the morning, hopefully some of these work. These lab hours, I'm prioritizing this class. So those are hours I'll be either in my office or in the collaboratorium. But if you have, you know, issues with your lab work and stuff, you can always find me here and get my help. And I'll give priority to lab students, that's you, over sort of my other classes during those hours. So you can find me during office hours or anytime I'm around. You can find me and ask for help. Or you can email me, or you can post on the discussion area of Canvas. Right, all three are good options. All right, so Canvas, so I'll let you read 8 things to know about this course. It's just some wisdom from the past that might or might not be useful. Link to lecture videos, so if you click through on that, you'll get a complaint from Canvas, but just go ahead and follow through, and that'll take you to a playlist. So there's the first half of this course, of this class today. Some useful 250 videos. So these are videos that mostly Izad has put up related to 250. There's a lot of stuff on here, so you have to go pretty far down to the bottom to get to the earlier stuff. For example, how do you use the lab equipment, which is part of what Lab 1 is. We'll talk about it a little in here, but you may want to find videos on here, and I may go through and dig out the relevant videos for that lab and post them somewhere. There's a video I put together a while ago on using a proto board, those little white plastic boards with all the holes for building circuits. We're going to be using those a lot. We'll have some circuits where we use like 3 of them. So there's a review if you need it. And then, yeah, labs, homework, midterm, finals. So that brings us up to labs. So let me talk about lab 1. Yeah, okay, I'll just take it from here. All right, so lab 1 is, it's a little bit of review. It's mostly getting familiar with some of the equipment that you'll be using this course. Some of this, like the power supply and the multimeter, should be familiar from 120. There's other equipment, the oscilloscope and the function generator, that may be new to you. So you're going to play around with these. So a handful of experiments. Experiment 1. Power supply, oscilloscope, function generator, and multimeter. So 4 steps, 1 for each. So basically, draw a simplified picture of the device, and look at what the basic controls are on it. So the power supply, normally you just turn it on, you set the voltage, you hook it up, and you go, right? It's got a whole lot of other buttons on the front. So dig into those, see what they do some research. I'll post links to some videos, but you can do online research by looking at the model number on these things. And you can do some experiments and just sort of try to document some more of the controls. That little button that says current or voltage, that little slide thing, what does that do, right? What's that knob that you turn when it starts clicking that makes it stop clicking? Stuff like that. So do that for the power supply, do it for the multimeter. You already did this for the multimeter in 120, I think. And then the function generator and oscilloscope, the same thing, but like I say, those are going to be new for a lot of you. So we'll talk about those a little bit. So that's experiment 1. It's just kind of like eyeballing some of this stuff. Experiments 2 through 4 are just working with the function generator and oscilloscope. So you're basically going to hook these 2 pieces of equipment together, and you're going to set the function generator in different ways, and you're going to observe what's happening using the oscilloscope. That's the high-level description, and I'll tell you about the details in a moment. But it says sketch the waveform on the oscilloscope and describe the variation from the ideal square wave, and do the same thing at these different frequency settings of the function generator. So what I would expect to see when I'm looking at your lab report is a description for experiment 2 saying, okay, we set the function generator to a square wave with a frequency of this, blah, blah, blah. We hooked it up to the oscilloscope. Here's the waveform we saw, and there's a picture of the waveform. And this was different from the ideal square wave because blah, blah, and blah, right? So you want to address the things that are asked for in each of the experiments. Experiment 3, we repeated the above experiment, but we set the frequency to 10. Here's a picture of the waveform we saw. There's your sketch. This differed from the ideal square waveform because blah, 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 and so on. Experiment 5, mapping the protoboard connectivity. That's a 120 lab. So you get the protoboard, and you use your multimeter, and you measure resistance, and you find which holes are connected to which, and somehow draw a picture of that. And if you draw, a box with some circles and some lines, make sure the person reading the report knows what that picture means. Right, here's the protoboard. The lines represent holes that are connected to each other, or whatever. And then experiment 6 is going to be the traffic signal control system. And this is going to be part 1 of a multi-part experiment that you're going to do in multiple labs, leading up to a full-blown 3-way traffic light, including yellow lights and a delay. All right, so let me talk about oscilloscopes and function generators first, and then we'll talk about traffic light control, and then we'll go ahead and get you to sign up for lab groups. So I'll try not to forget that. So function generators are pretty straightforward. Function generator is a box, and it's got some dials on the front, and it's got some switches, and it's got a pair of outputs. And basically, this thing will generate things like a sine wave, or a triangle wave, or a ramp, or a square wave. Right, so power supplies just put out 5 volts. 5 volts, 5 volts, 5 volts. How you feeling today? 5 volts, right? Function generators put out a signal that changes over time. So it could be a sine wave. Mostly we're going to play with square waves. Why? Because they're nice and digital. 0, 1, low, high. Whereas sine waves and these things are more analog. But a function generator is capable of generating all these different shapes. Okay, so what do you want to change when you're producing a wave? Well, you want to change its shape, sine wave, triangle, and so on. You can change its frequency. So frequency is how often something happens. So this is one frequency of a sine wave. This is a higher frequency. It's changing between high and low at a higher rate. This is a lower frequency. Changes very slowly. If you turn this into pressure waves, this is a high-pitched tone, this is a low-pitched tone. Both of these waveforms have the same distance between the highest part and the lowest part. Right? So there's the frequency, but there's also the amplitude. So amplitude is how big the waveform is, how tall it is, how much it changes between the highest voltage and the lowest voltage, completely independent of frequency. And you can adjust the amplitude with this function generator, you can adjust the frequency. There's a thing called DC offset, but I don't think it's adjustable on the function generator, so don't worry about it. DC offset basically says right, certain frequency, certain amplitude, exactly the same frequency, exactly the same amplitude. But this goes, say, from positive 1 volts to negative volts. This goes from positive 2 volts to 0 volts. So it's been shifted up a little bit. Okay, that's what we call a DC bias or a DC offset. But I don't think it's adjustable on your function generators. Okay, so function generator is just a box that makes all these different types of waveforms, lets you control things like frequency, amplitude, and so on. A multimeter will not help us in looking at these waveforms, because if you hook this up to a multimeter, your display just changes numbers rapidly. It'll show 0.7, negative 0.2, negative 0.6, 1.3, and it just bounces around a few times a second. So an oscilloscope is a device that lets us look at these waveforms basically by drawing them for us. So, and I should use like the actual equipment that we have, but I don't have a picture of it handy, so I'll just do a generic oscilloscope. So there's a fairly fancy oscilloscope. And it has various knobs on it for controlling how we want to display this waveform. It's got a big display usually over here on the left that actually shows us a picture of the waveform. And it's got some inputs down here where we feed the signal in that we're trying to display. So how does this work? Let's just look at the display. So imagine that this is a wall of concrete. Okay, it's a hot summer day. It's a white concrete wall, and you have a garden hose, and you can spray the hose on the wall, and wherever the water hits, it turns dark, right? So you take your garden hose and you point it right here in the middle of this left section of the wall, and you slowly start to move the hose over to the right. Okay, if you do that, you're going to get a line going across the middle of that wall. Forget about the water dripping. You're just going to get a line across the middle of the wall, right? Now imagine that while you're moving this hose across, somebody is giving you instructions on how far up to raise your arm. Okay, put your arm level, now raise it up a little bit, keep raising it up, now drop it down, now start raising it up again. And as you do that, the place the water hits is going to change. Well, if those instructions being given to you are right, you're going to get a picture of, say, a sine wave. Or if somebody says, okay, hold your arm right at eye level and keep it right there. Okay, now raise it above your head and hold it right there. Okay, now come back down to eye level. Okay, hold it right there. Now raise it above your head, right? Then the pattern on the wall would look like that. And every time you get to the end, you're going to turn off the water really quickly, move your arm back here, and then turn the water back on. And you're going to start the process again. Okay, that's effectively what happens inside an oscilloscope. Old days, it used to be an electron beam hitting a cathode ray tube, and now it's all done digitally. But that's the effect of it. So the thing giving the instructions on how far to raise your arm, that's the signal that you're trying to draw. So that might be what's coming from the function generator, and depending on the voltage going in, this beam gets raised or lowered a certain amount. And so in effect, you get an exact image of what your waveform looks like. So what are the variables? Well, how quickly do you move from one side to the other? If you move very slowly, you're going to get a bunch of up and downs right next to each other. Your waveform is going to look really squished up. If you move really fast, by the time you go from one end to the other, you might have raised your arm that much. You're going to get a very slow change. Okay? So you can change how much this waveform gets spread out by adjusting how quickly this moves across. So we can basically adjust the frequency that we're looking at. So if we have a high frequency, we can change how quickly we sweep, and we can still see the waveform, so it looks like that. And we can change the amplitude, because if someone's putting in a very weak signal, you might only move up and down that much. And so we can say, okay, well, if you get a little bit more voltage, I want to go all the way up here. And if you get a little bit of negative voltage, I want to come all the way down here. But now if you're getting a signal in that's going between, say, 0 and 100 volts, right, we could say, okay, so 100 volts, I want to put it up here, and 0 volts, I want to put it down here, and we can scale it down. So the oscilloscope will let you adjust the frequency and the amplitude and the DC offset so that you can look at your waveform however you want to see it. Now the dirty secret is there's a button on top called Auto, and if you press that, it kind of does all this for you. And I didn't even know it. I saw some students doing it once, and I'm like, whoa, that's cool. But that's what's going on inside, okay? And you can use all the knobs to set this stuff manually. And they're a lot of fun to play with, actually. I had one when I was a kid, and it used to just be like endless amounts of entertainment. But that was me. All right, so these experiments, set up the function generator, hook it up to the oscilloscope, and observe the waveforms. All right, let's talk about traffic lights. So we're envisioning a three-way intersection. And this is not written out in the lab, but I would like you to draw your intersections like this, with the T coming down, and I would like you to think about identifying these roads in terms of compass directions. So this is west, or W, this is south, or S, and this is east, or E. And this is going to work a whole lot better than identifying these as like 1, 2, 3, or A, B, C, because that's really ambiguous. And anytime we talk about this in class, I'm going to draw my intersection like this. This is going to be west, south, and east. So if you want to take the work you're doing and somehow correlate it to what we're discussing in class, you probably want to use these labels, this orientation. All right, so there's a three-way intersection. It's basically a single lane, so we don't have two lanes. Cars can go wherever, and they just share the road. so it's a little simplified. And there's a signal for each lane, which is either green or red. So there's a light over here, which can be green or red. There's a light here, which can be green or red. And there's a light here, which is green or red. And there's also a set of sensors, one per lane. So right-of-way laws say the car on the right gets priority if there's two cars at the intersection. So if there's a car sitting here and here, the car on the east gets priority. If there's a car sitting here and here, the car on the south gets priority. If there's a car sitting on the west and the east, we're still going to say car on the east gets priority. Okay? And if there's only a car on one section, they just get permission to go. So ultimately your goal is going to be to build a circuit that controls the lights, red and green, on each lane based on what it's reading from the sensors. And so if there's a sensor reading here that says there's a car on the east, that should give east a green light and everyone else should be red. And so on. But we're going to build this up over a series of labs. So for this lab, this experiment 6, you want to do the following. Draw a picture of that intersection, right? Label the lights and label the sensors. And does it ask for a system diagram? It should. Well, inputs and outputs. Okay, so raise your hand if you know what a system diagram is. Okay, system diagram is a 40,000 foot view of a circuit. It's basically saying, here's the inputs, here's the outputs. I don't care what's going on inside this box. I'm not specifying that, right? I'm just saying I'm giving you a box. Here's the inputs, here's the outputs. And what does this box do? How do inputs get changed into outputs? What outputs correspond to certain inputs? But it's not describing, well, I've got an AND gate and some wires and a resistor and all this other stuff, okay? It's just looking at it in terms of a functional unit. This is what goes in, this is what comes out. Okay, so for this lab, you want to basically think of this in terms of a system diagram. What are the inputs? Well, you got 3 sensors, and you've got 6 outputs, 3 lights, 3 greens, 3 reds. Okay, so your system diagram, 3 inputs, 6 outputs. And how do we describe how inputs correspond to inputs? That's a truth table. So a truth table, you have a list of inputs for each possible combination, you list the corresponding outputs. So you want to develop a truth table that corresponds to this intersection. And it'll probably look familiar to something you did in 120. Something involving airplanes. Okay, so that's experiment 6. It's sort of a warm-up on the traffic light. So sketch the intersection, label the inputs and the outputs, draw a system diagram, and then make a truth table. Okay, so now let's talk about lab reports, right? Labs, some of the labs in here take a long time. Some of them, the circuits get really complex. It's not unusual to spend several hours on some of the last labs, okay? That's a lot of work. I don't have a way of going in and watching each person spend several hours working on their lab and see what they're doing and what's their circuit look like and so on. It would be great if I could, right? The only way that I have of grading you on your labs is your lab report. So your lab report has to contain all the information that I need to know what you did in your lab, right? So it's got to have a lot of detail. It's got to be written in such a way that if I wanted to reproduce your work, I could do it from your lab report. And this is the nature of scientific papers, right? How do we do science? We do an experiment, we write it up, we publish it, other people reproduce our work. And after 50 people have done the same experiment and got the same results, we have a theory. When you do this, that's what happens. Or somebody does my work and they get a different result and they say, you know what, I think there's something else going on. Okay, that's how science works. So you want your reports to be written in such a way that somebody else could take your report and reproduce your work. Which means you have to describe exactly what you're doing in the report. So let's look at experiment 2. Right, you're sketching a waveform on an oscilloscope and describing variation. Suppose you do that, but you don't mention that you set the square wave to 1 kilohertz with an amplitude of 5 volts. All you've said was experiment 2, and here's a picture of a waveform. Can somebody else reproduce what you did? No. Because they don't know everything that you did. Same with the protoboard connectivity. You have a beautiful picture of the protoboard with some lines drawn between the holes. Can somebody else do what you did by looking at that picture? No. You can say the lines represent holes that are connected to each other. Well, can they reproduce your work? No. How did you get those lines? How did you decide where the lines were? Well, we used a multimeter and we set it on resistance and we put wires into different holes. And we looked at the ones that had 0 resistance and we drew lines on the picture to show what was connected. Oh, okay, now I can reproduce what you did and see if I get the same result. Okay, you got an idea what kind of level of detail I'm looking for? So it's not just having more words or more pages, it's having information so that somebody can reproduce the work that you did. That's the real goal. So if you draw a traffic intersection, you have a truth table, and your truth table inputs are labeled A, B, C. What are A, B, and C? What do they mean? Well, A is the sensor for the car coming from the west. Got to say that, right? And what does a 1 mean if A is equal to 1? Does that mean there's a car, or does that mean there's no car? Got to say that. Because I might have a sensor that generates a 0 when a car shows up and a 1 when there's no car. So constantly keep thinking about these kinds of details. You're going to be working with this stuff so much, it's all going to be obvious to you. But at some point when you're writing the report, you got to step back periodically and say, is this obvious to the person reading this who's not me? Okay, and that's a really useful exercise in terms of thinking about what you're doing and why you're doing it. So that'll actually help you with understanding. All right, so there's a short sentence here on report requirements, but I have a longer one. So on Canvas, there's this guide to writing up lab reports. And this is also new for this quarter. I've never done this before. In the past, I've said, I don't really care how you write your lab report as long as you have all the necessary information. And by and large, the reports don't have the necessary information. So I'm trying something different here. I'm going to give you very detailed requirements for what I want you to write up in your lab report. So again, general guidelines, typed or computer printed, okay, no handwritten reports. The one exception is circuit diagrams, figures, pictures. Don't spend your life trying to figure out how to draw a circuit on your computer so it looks nice. Just get a piece of graph paper, a nice pencil, maybe a straight edge, draw it by hand, scan it in. Okay? If you don't know how to scan in a picture so that it's legible, let's figure it out. Okay? Start a discussion on Canvas or shoot me an email. These are really good things to know how to do. Okay? If you have a smartphone, that's usually a pretty good start, but you really want to make sure what you have is legible. So you might want to download some software. There's tons of free software out there to do things like crop pictures or line them up or things like that. And we can talk about this. But you're building a toolkit of ways to do things like prepare reports, right? Or if you're computer science, ways to debug programs and so on. So build your toolkit. All right, so lab reports get submitted as a PDF. Okay, and most word processors, Word, LibreOffice, OpenOffice, will let you export as a PDF. Don't ever turn in a doc file. Doc files are the most unreliable way to pass information around. Because if my version of Word is different from your version of Word, I'll get your doc file, and it's going to have figures in weird places, and the fonts will change, and all this kind of stuff. PDFs are designed to be portable. That's the P in portable document format. It's also less likely that I accidentally lean on my keyboard and I modify your document. You send someone a doc file, and unless you protect it, right, it can be changed very easily, accidentally or intentionally. So it'll only accept PDFs on Canvas for lab reports. Lab reports get individually written. Okay, again, you do the work in groups, but you write up your own report. And things like circuit diagrams, tables, that kind of stuff, everybody has to write their own. Okay, and that's going to be a pain in some of the later labs because the circuits will be huge, and it will take you, 20 minutes to draw the circuit. It's important to make sure you do it. Okay, because you're going to see this on exams, and you don't want the exam to be the first time you try to actually draw this circuit. And everything in the lab report should be in your own words. If you feel like you need to take something verbatim from the report or from the textbook or something like that, you got to cite it. Okay, you've got to somehow refer to it somewhere else and say, this was taken from such and such, and list what that source was. Okay, that gets into the area of plagiarism. And some places will have a zero tolerance towards that. If you turned in a paper and it had a sentence that was taken from somewhere else and somebody finds that, it can have serious consequences. Okay, I had a friend who was called before the honor board because she had 3 words that were taken verbatim from another source. They were very common words. It was like the total concentration or something like that, and somebody said, oh, here's a paper that uses those same 3 words. And they ended up in front of the honor board. They were exonerated, but they had to go through a lot of. So it's taken pretty seriously in science. All right, so formatting. I want to be able to see where one section begins. Okay, so get familiar with section headings. Every word processor has a way to do this. I do not care, if you use uppercase, if you use Roman numerals, something like that. If you just want to have an uppercase title and some space around it, that's fine. But something that differentiates one section from another, one experiment from another. Okay, so general organization. A cover page. And the cover page should have the following: the title of the course, the number of the lab, your full name, okay, first name, last name in that order, and then a line that says lab partners, and the full names of each of your lab partners. Okay, and that's really important. I've had cases where the cover page has 3 names on it, and the 3 lab partners shared that cover page, and now I've got 3 lab reports with the same 3 names in the same order. I don't know whose report is whose, right? So separate line that says lab partners, followed by the names of your lab partners, so it's clear who the author of the paper is and who the lab partners were, and then the date on which you write the report. Okay, that's all that's on the cover page. And then the second page begins with a section called Introduction. And it can just be one sentence that introduces the whole lab. Okay, so for lab 1, what's the basic description of this lab? We're working with some test equipment and familiarizing ourselves with some of the basic concepts related to Engineering 250. That's a good introduction. And we're starting the design of a traffic light. Right? So somebody reading this, they can just read the introduction and know what this report is about. Okay, that's before you start in with experiment 1 or anything like that. Okay, so an introduction to the whole report. And then I want a section called experiment 1. And you go ahead and you describe experiment 1. So experiment 1 should have the following sections: an overview of the experiment. Okay, so in experiment 1, I don't remember what experiment 1 was anymore, but in experiment 1, we're building a circuit and measuring some voltages, blah, blah, blah. A section that talks about basically why you're doing this. What's the purpose? What's the theory that we're trying to develop here? Okay, this is going to take some thinking about, but instead of just doing what I did in school, which was just blindly go through the steps and turn it in, try to think about why you're doing this, right? What are we hoping to learn from this particular experiment? What concept are we testing? We're working with Ohm's law. We want to verify that Ohm's law works. So something about objective and theory. And then a section on procedure, which basically says, what did we do? Okay, we built the following circuit. Here's a picture of the circuit. We connected 5 volts to the power supply. We used a multimeter and measured the voltage across the resistor. Here's the value that we got. Okay, so procedure, observations, those might get mixed together, but you've got to have description of what you did and then everything that you observed, right? We switched this wire here and the resistor started to smoke, and my friend touched it and he said, "Ow." Okay, it's a good observation to have. And then a section on results and discussion. So anything that the lab itself asked you to do, right? Talk about how this deviates from the ideal square wave, right? You can put this in here also. And then go on and do another section, experiment 2, same pieces. Okay, so all your experiments basically have the same subsections to them, and it's got all these pieces in here. And this will help you make sure that you're not skipping over something, right? So you get to the results discussion, that's where you can go back to the lab and say, oh yeah, and it wanted us to talk about what happens if we switch these 2 wires around. We forgot to do that. Okay, so you can go back and put that in. Switching the wires around had no effect. Okay, that's a cool conclusion. All right, and then at the end of all those sections for experiments, you want a section, conclusions and lessons learned, for the entire lab. Okay, you just spent 2 hours doing all these experiments. What's the punchline? What's the takeaway? What did I learn from this? What can I conclude from this? So something that wraps up the entire lab. And then the last section is one called New Experiment. And this is one that Izad always insists on, and I think it's a really cool idea. You've got a lab, so lab 1 has 6 experiments to it. Your goal is to come up with an experiment 7. Okay? And the idea is, what was common from these 6 experiments? What was the basic theme here? Or some set of them? And what would be a cool additional experiment that would take these concepts even further? Because you're supposed to be learning something in these experiments, right? They're not just busy work. They're supposed to be giving you hands-on experience with some set of concepts or ideas. What would be a cool additional experiment? Okay, this is probably the hardest thing to come up with in the whole report. And it's worth spending, you know, a half hour maybe trying to come up with a good new experiment. Don't just lowball it and say, okay, repeat that experiment but set the frequency to 20 hertz instead of 10. Yeah, it's a new experiment, but it doesn't really take you in a different direction. Okay. So what could you do that would somehow deepen your understanding of what's going on? And you need to write it up like these other experiments. So, for example, you know, experiment 2 has a lot of detail to it, right? So experiment 7 should not be something like build an amplifier, right? Or build a circuit that turns lights on and off every second.
I'm looking at experiment 3 and 4, and I feel like that it's hard to put a lot of information in 3 and 4 unless.
Yes, so 3 and 4 are variations on experiment 2. You don't want to do a variation on an experiment for a new one, though. So if you said experiment 7, repeat experiment 2 with the frequency set to 20 hertz, that's not a good new experiment. Okay.
I'm talking about putting a lab report, though. Yeah, when you put in a lab report, you don't want to repeat the entire process like.
Oh, no. So you can say, you know, we repeated experiment 2, but we set the frequency to 10 hertz. That's fine for a description of the procedure. As long as it's easy for the reader to take what you've written and understand what you did, basically.
So don't try not to be redundant.
So for the new experiment, yeah, try not to be redundant. And like I say, that takes some thought. And you need to put in enough detail so that if somebody else read your description of experiment 7, they could actually do it. Okay, so we don't give you experiments where we say, build a circuit and measure the voltage. Right? We say, build this circuit, measure the voltage at this place. Okay, so you need enough detail so somebody could actually do your experiment. And you also want to include what you expect the results would be. Now, you don't have to do the experiment yourself. Okay, but you should put a description of what the results would be if somebody did this experiment. What would you expect them to measure, observe, whatever it is the experiment is saying. Okay, does that make sense?
Yes.
So this is new. If there's something in here that's not logically consistent or something like that, that's very possible, okay? So in general, in this course or in any of my courses, right, if something's not making sense, ask, right? If I say one thing and then I say something else, you don't know which to do, don't just make a guess. Go ahead and ask, especially with something like this where this is the first time I'm doing these kinds of requirements. All right, so that's lab 1. You can get going on lab 1 anytime you want. It's due a week from today. Okay, so this coming Tuesday. Collaboratorium hours are posted, but it's open pretty much any time during the day, Monday through Friday. And if I'm around or Izad's around or if there's a lab assistant around, you can ask them for help. Yes?
Should we do lab partners?
Yes, thank you. Okay, we're out of time, so I'm going to post this on the inside door where the 250 lab kits are, and your lab groups are 17 through 24. So find 3 or 4 people that you want to work with, right? Group sizes of 3 or 4, and figure out, and then this will be in the door. Just go ahead and put your names down here for which group you're in. Thanks for the reminder. All right, have a good week. I will see you Thursday.